Hello and welcome to 3.7 Related Rates. In this section we'll be looking at some word problems involving the chain rule to figure out missing rates that are in our problem. Okay, so one of the things we will look at first is this problem with the cone. Okay, generally this is a classic problem. They give us a cone, and in a lot of cases water is either drained out of a cone or water is filled into the cone. Okay, and what we do is we figure out the volume formula first. Well, the volume formula is strictly from geometry. Volume equals pi over 3 times r squared times h. And then based on the equation and certain facts, we try to rewrite the equation in terms of one variable. It would make it easier. But let's do an example to demonstrate this. It says the variables x and y are both differentiable functions of t that are related by the equation y equals x squared plus 3. Find dy dt when x equals 1, given that dx dt is 2 when x equals 1. Okay, so if we're finding the derivative with respect to t, okay, that's gonna have us use the chain rule for both y and x. Okay, so if we just take the derivative with respect to t, y becomes 1 times dy dt equals derivative of 2x squared is 2x dx dt. Okay, so because y and x are foreign to t, right, they're different variables than t, we use the chain rule to help us solve it. Okay, so we end up with dy dt equals 2x dx dt. Okay, now they told us that x is 1 and dx dt is 2. Okay, so we just plug into our formula. X is 1 and dx dt is 2. Okay, and so to finish it off, we just simplify 2 times 1 times 2. So that would give us 4. Okay, very basic example, but you see how we end up using the chain rule for both y variable and the x variable when we're differentiating, because both of them are different variables than t. Okay, ripples in a pond. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles, as shown in the figure. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Okay, so if we're dealing with circles and we're dealing with area, okay, we're going to end up using some form of the area formula of a circle. Okay, we would say A equals, and this is the classic area formula, pi times radius squared. Okay, now one of the things we have to notice is they want us to figure out at what rate is the total area changing? Okay, the rate at which area is changing with respect to time would be dA dt. So that's what we're looking for. They're saying that the radius of the outer ripple is increasing at a constant rate of 1 foot per second. So they're giving us dr dt. That would be the rate at which the radius is changing with respect to time. And they're saying that's 1 foot per second. Okay, and then they're saying when the radius is 4 feet. So when r equals 4. Okay, so it's kind of good to just write down what's given and then what they're looking for. Okay, and then we could just go from there. We're given a general formula, a equals pi r squared. We can take the derivative, right, with respect to t. So a would become dA dt. Pi r squared, we just multiply by the 2, so it becomes 2 pi r and then times dr dt. Okay, and now we could just plug in. We're looking for dA dt anyway, so we just plug into the right side. 2 pi, radius is 4, and dr dt is 1. Okay, so this would be 4 times 2, that's 8. So dA dt it would be growing at 8 pi, and then the area would be square feet, right? So this would be square feet per second. Okay, so general guidelines for solving these related rate problems. Identify all given quantities and quantities to be determined. Okay, so that's what we did in the beginning, right? We identified what was given and what we need to find out. Okay, if you don't have a sketch, make a sketch, label the quantities. Write an equation involving the variables whose rates of change either are given or are to be determined. Using the chain rule, implicitly differentiate both sides of the equation. So take the derivative of both sides with respect to t. After completing step 3, substitute into the resulting equation all known values for the variables and their rates of change and solve for the required rate of change. Okay, so pretty straightforward. So this table lists some examples of mathematical models involving rates of change. For instance, the rate of change in the first example is the velocity of a car. Right, velocity of a car after traveling for 1 hour is 50 miles per hour. Okay, x is the distance traveled. dx dt would equal 50 when t equals 1. Water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. Okay, so that's 10 cubic meters per hour. That's a value for the volume. Okay, and that rate would be dV dt. Okay, a gear is revolving at a rate of 25 revolutions per minute. Okay, 1 revolution is 2 pi radians. Okay, so this would be relative to theta, d theta dt. Okay, in terms of the angle of revolution. Population of bacteria is increasing at a rate of 2,000 per hour. Okay, so if x represents the population dx dt would be the rate at which the bacteria is increasing. Okay, so let's take a look at an inflating balloon. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. Okay, so air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. So that's a unit of volume. That means this is dV dt is equal to 4.5. Find the rate of change of the radius. So that's dr dt. That's what we're trying to find when the radius is 2 feet. Okay, so now if it's a spherical balloon, we would go off of the volume formula for a sphere. Okay, now the volume formula for a sphere is 4/3 pi r cubed. Okay, and so now what we do from here, we take the derivative, so we would get dV dt equals, take the exponent, multiply in front, 3 times 4/3 pi, drop the power by 1, times dr dt. Okay, so we're given dV dt is 4.5, so now this 4.5 equals, radius is 2 feet, so we'll plug in 2 for the r. We can cancel the 3 here with the 3 in the denominator. Okay, so we have 4 pi 2 squared, and then dr dt. Okay, so you have 2 squared is 4. 4 times 4 is 16. So 16 pi dr dt. And that's what we're solving for. We're solving for dr dt. So divide both sides by 16 pi. Okay, that way you get the dr dt by itself. And then 4.5 divided by 16 pi, this will be approximately, if we put it into the calculator, 0.09 feet per minute. Okay, so the radius would be growing at that rate. Okay, let's take a look at the speed of an airplane tracked by radar. An airplane is flying on a flight path that will take it directly over a radar tracking station as shown in the figure. The distance s is decreasing at a rate of 400 miles per hour when s equals 10 miles. What is the speed of the plane? Okay, so it's kind of set up in a right triangle scenario. Okay, they tell us that the vertical distance to the level of the airplane in the sky is 6 miles. They also tell us that s is 10. They say that the distance s is decreasing at a rate of 400 miles per hour. So ds dt would be equal to, and it's decreasing. Okay, so I would say that's negative 400 And then what are we looking for? What is the speed of the plane? So now the speed of the plane, that would be the rate at which x is changing. Okay, so we're looking for dx dt. Now one of the things we have to find out to get this to work is x. Because right now the way we could set this up is a Pythagorean theorem. Right? For Pythagorean theorem we would have x squared plus 6 squared equals our hypotenuse s squared. Okay, now x we could easily solve for. They tell us s is 10. So if s is 10, we could use x squared plus 6 squared equals 10 squared. That gives us x squared plus 36 equals 100. Subtract 36 from both sides. So x squared equals 64. So x equals 8. Right? Take the square root of both sides. Okay, so we also know that if s is equal to 10, x is equal to 8. Okay, and now we could take our derivative and solve for dx dt. Okay, so take the derivative with respect to t, power rule, so 2x dx dt. Now this is 36, but derivative of a constant is 0. Okay, so we don't have that in our derivative formula. And then 2s ds dt. Okay. So let's plug in. We know that x is 8, so we have 2 times 8. We're looking for dx dt. And then we have 2, s is 10. ds dt is negative 400. Okay, so we have 16. Okay, so we have 16 dx dt equals, that's negative 4,000 times 2, negative 8,000. Okay, divide by 16. So that means we get dx dt this would equal negative 500 miles per hour. Okay, so this would be the velocity of our airplane coming to the west. Okay, so the speed would be the absolute value of the velocity. So the speed of the airplane, just take the absolute value, would be 500 miles per hour. Okay, so just make a note, if they ever ask you for the speed, speed is the absolute value of the velocity. Okay. Let's take a look at example 5, a changing angle of elevation. Find the rate of change in the angle of elevation of the camera shown in figure 3.40 at 10 seconds after liftoff. Okay, so the camera is out here, and we're looking at the change in the angle of elevation. So we're looking at d theta dt at 10 seconds after liftoff. So t would equal 10. Okay, so one of the things looking at the figure, we have 2,000 feet, so the camera is 2,000 feet from the launch pad. And then we have, what else? Right, so they're saying that tangent of theta is equal to s over 2,000. So what would that mean? Based on this theta, tangent would be opposite over adjacent. So this is what they're saying is s. Okay, so now they say here a television camera at ground level. Okay, so this is important as well. Just read the caption. Is filming the liftoff of a rocket that is rising vertically according to the position equation s equals 50t squared, where s is measured in feet and t is measured in seconds. The camera is 2,000 feet from the launch pad. So the first thing we could do is figure out what's the height, what the s is when t is equal to 10, because they give us this formula for the position. Right, so they give us s equals 50t squared. So if t is 10, plug 10 in, that's 100 times 50, so s is 5,000. Okay, so that's important. Now, we're going to be using this tangent equation to help us solve the problem. One of the things we're going to need is, as we take the derivative of s, we will need ds dt. Okay, now looking at our derivative here, derivative of s with respect to t, well, we just use the power rule. 2 times 50, that's 100 t. Okay, and that would be our ds dt. Okay, that's when it comes time for that piece. Okay, so let's use our tangent of theta equals s over 2,000. Okay, take the derivative of both sides. Now, if it helps you, just rewrite this s over 2,000. I would say put it like this: 1 over 2,000 times s. So the 1 over 2,000 is like a coefficient. Okay, so now take the derivative of both sides. So derivative of tangent is secant square theta d theta dt equals 1 over 2,000, and derivative of s is 1 times ds dt. Okay, so now we could plug in, we're looking for d theta dt. Okay, and we have ds dt is 100t. Now one of the things that would help us here, secant squared is the same as 1 over cosine squared d theta dt. Okay, equals 1 over 2000 now ds dt is 100t. Okay, now to get the d theta dt by itself, I can multiply both sides by cosine squared theta, right, so that those cancel. So I have d theta dt equals, let's put cosine squared theta, I'll put the 100t times 100t over 2000. So one of the things we have to plug in actually is the cosine of theta based on our triangle, right? We never declared what cosine of theta would be, but we didn't know in the beginning until we got to this point where it says where it says cosine squared theta. So that's okay. So declare what cosine of theta is based on our triangle. So cosine of theta is adjacent over hypotenuse. Okay, so how do we figure out that? Adjacent is 2000 over, now how do we get the hypotenuse? Well, generally this is 2000 squared plus s squared would equal our hypotenuse squared. And so the hypotenuse would be the square root of 2000 squared plus s squared. Okay, that's the hypotenuse. So this would be our expression for cosine. Now, picture that being squared. Okay, so we're going to plug in for the cosine, and then we're going to square it. 2000 over square root of 2000 squared plus s squared. Put that in parentheses and square it times 100 t over 2000. Okay, now we have values for t and s. That's going to help us finish this off. So we know that t is 10 and s is 5000. Right, t was given to us and we figured out s early in the problem. So just plug those in now. Okay, so we have 10 will go here and the 5000 will go here. So if we square this, our top becomes 2000 squared over squaring the square root, so you no longer have a square root then. 2000 squared plus 5000 squared times 10 times 100, that would be 1000 over 2000. Okay, so one of the things you could do to make it a little simpler, you have a 2000 squared and then a 2000 here in the denominator. Cancel out the 2000 with one of the 2000s there. Okay, so you have 2000 times 1000 on top. Over 2000 squared plus 5000 squared. Okay, do the math on that. Okay, and then you end up with about 0.0689 radians per second. Okay, so that's it for our lesson. Any questions, just let me know. Okay, email me. Have a good day. Have a good night. We'll see you soon.